Have you ever wondered how scientists precisely measure the invisible movement of water from the Earth's surface back into the atmosphere? Understanding this process, crucial for global water cycles and climate, requires specialized tools. Eddy Covariance, often abbreviated as EC, is a powerful micrometeorological technique used to directly quantify the net exchange, or flux, of gases and energy, including water vapor, between an ecosystem and the atmosphere. Specifically for evapotranspiration, or ET, flux measurement, EC precisely determines how much water leaves the surface as vapor through evaporation from surfaces and transpiration from plants. The fundamental principle behind EC relies on measuring the rapid fluctuations of vertical wind speed and the concentration of a scalar, such as water vapor, in the air directly above a canopy or land surface. These turbulent fluctuations, or eddies, act as tiny transporters, carrying water vapor upwards or downwards. By simultaneously measuring how fast these eddies move vertically and the amount of water vapor they carry, EC calculates the average vertical transport of water vapor over time. This method captures the turbulent mixing layer near the surface, allowing for direct measurement of the flux without disturbing the natural environment. To implement eddy covariance, specialized instruments are deployed, typically on a tall tower, allowing them to sample the atmosphere above the target ecosystem. These include an ultrasonic anemometer that measures three-dimensional wind speeds at very high frequencies, usually 10 to 20 times per second, and a fast response infrared gas analyzer. The gas analyzer measures the concentration of water vapor and often carbon dioxide at the same high frequencies. The raw data from these sensors are then processed using complex algorithms to account for various environmental factors and instrument characteristics, ultimately yielding the accurate ET flux value. A key advantage of eddy covariance is its ability to provide continuous, high-resolution measurements representative of a relatively large area, known as its flux footprint, without physically enclosing the ecosystem. This non-intrusive approach captures the integrated response of natural systems to environmental changes. This makes EC indispensable for validating satellite-based remote sensing models, providing ground truth data for regional and global climate models, and understanding ecosystem water use efficiency. It offers a direct window into the dynamic interplay between the biosphere and atmosphere. Ultimately, eddy covariance offers an unparalleled method for understanding the vital role of evapotranspiration in the hydrological cycle and its response to environmental shifts. This robust technique allows researchers to track the pulse of ecosystem water exchange, providing critical data for managing water resources, predicting climate impacts, and informing agricultural and ecological practices globally.
If you love learning about water, like, subscribe, and keep exploring with us.